So my name is Boris Blinov. I'm a physics professor at the University of Washington in Seattle. I've been here at the University of Washington since 2005, first as an assistant professor, then as an associate professor, and as a full professor. Before that, for about 5 years, I was a postdoctoral fellow at the University of Michigan in Ann Arbor, Michigan. And that's also where I got my PhD degree. So I was there for 5 years prior to that. And then my undergraduate degree is it's all in physics from Moscow State University in Moscow, Russia. So I've been in the field for a long time.
And then how did you get interested in research in the first place?
I was interested in various types of experiments since probably middle school. It was mostly chemistry that I was playing around with, mixing things and not really blowing up things, but at least, making things bubble and change color. And along the way, I learned why this was going on, what was the chemistry that was happening. And then chemistry somehow led me to physics, even though initially I was interested in doing kind of theoretical work in physics, but then I quickly realized that I liked doing the experiment more, so I switched to doing experimental work. And also, my family, two uncles are physics professors as well back in Russia. So I grew up surrounded by scientists. So I guess it's sort of a family thing.
Yeah, okay. And then in terms understandable to a high schooler, could you give me an overview of your research?
I can try. So my current research is in the area called quantum computing. And you may have heard about this, and there's a lot of buzz. There's a lot of, well, I guess I'm paying attention to it, so it seems like a lot. It's basically a new way of doing computation compared to what we are used to. Computers are ubiquitous and they're very good for doing a lot of things, a lot of tasks that are very hard for humans. But there are also tasks that are hard for our everyday regular computers. They may seem exotic, but they are important. And it turns out that if we use a different way of doing computation, the way that involves quantum physics, then at least some of those tasks become doable. They don't become easy, but with a quantum computer, it would be possible to do. So one of these range of tasks, computational tasks, has to do with the working of the matter on a very fundamental level of atoms. For example, photosynthesis. It's a process by which energy of light, of sunlight, is converted into chemical energy by plants. And then that energy is stored, and that's how the plants grow, and eventually we all get our energy from the sun, even though it doesn't seem like it's the way it is, but all of the energy that we have comes from the sun thanks to the plants. Anyway, so photosynthesis is extremely efficient. It's very finely tuned process, and we don't understand how it works. If we're able to reproduce it, we would be able to do what plants are doing and convert solar energy to. So like solar panels are good, but not very good. Their efficiency is very low. So we can get a lot of energy that would be clean, green, and anyway. And so people have tried to understand scientists have tried to understand how it works, but not successfully. But there's hope that with the use of a quantum computer, we would finally be able to understand that. And that's just one example. There are many examples that are similar.
That's super interesting. And then what's one of the biggest challenges that you faced in research and how did you overcome it?
Well, there are many challenges. So I'm doing the experimental work in this field and sort of fundamental work, not trying to build a working quantum computer, but that's because that would be a very difficult engineering challenge. But we're trying to solve the basic problems. The analogy you may use is the analogy between regular computers that we use and the quantum. So we're trying basically to figure out how to build a transistor. A quantum transistor. It's not really a transistor, but it's the same basic element of a quantum computer that a transistor is a basic element of a regular computer. So the challenges are typical for an experimental physics work. We're using a lot of sophisticated equipment that is not really sort of consumer grade that you turn on and it works. No, you turn on and you turn something else on, you turn a bunch of knobs, and you adjust a lot of things, and finally it may work. So getting these things to work is probably the biggest challenge in the practical aspect. In the more fundamental aspect, the challenges are basically controlling these quantum systems is extremely hard. You know, if your knowledge of quantum comes from the Marvel movies, the quantum realm, that's very deceiving. It's not a small world. The entire world is quantum, but on the small scales. Anywhere you look, if you have a powerful enough microscope, you'll see quantum effects. But these quantum effects are very delicate and very fragile, and controlling quantum states is just difficult. And that's actually the main challenge of quantum computing these days.
And then, what do you enjoy most about your research?
Well, my research involves working with lasers, and that's actually one of the control kind of tools that we have. Laser light is a kind of extreme in many ways. It's very direct. That's the main thing that people know. It's just, you know, shining in a very well-defined direction, a very small beam that goes far. But it also is the term is monochromatic. It has just one color to a very, very high degree. So you might know that the rainbow that we see is caused by the sunlight being refracted, and the rainbow shows the range of colors in the sun. Well, we see the sunlight as basically white, but it actually is a mixture of all these many, many, many colors. So if you take a rainbow and zoom in and zoom to just one single color in that rainbow, that's what basically a laser light is. It's very pure single color. And these colors are beautiful. And when you work with lasers in your lab, you have various little mirrors and lenses and other optical devices that you direct the light with. And to me, that's just the biggest enjoyment, working with laser light.
That sounds really cool. And then, which person or mentor in your field has made the biggest impact on you?
I think the biggest impact on me was by Professor Christopher Monroe. He's at Duke University now, but back then when he was my mentor, he was at the University of Michigan. Basically, I learned a lot from him, and I tried to apply it to my own work as a professor here at UW. I don't know how successful I was, but he's actually a very well-known person in not just quantum computing world, but outside. He's one of the founders of a quantum computing company called IonQ. He was also one of the three scientists who basically testified to Congress in 2015, I believe. The result of that was a huge amount of funding for quantum computing research that the federal government made. So yeah, I guess he was probably the biggest.
And then, were there any pivotal moments in your research career that made you change topics or want to pursue a certain topic?
The most important one happened after I finished my PhD. So my PhD work at Michigan was actually not in this, it was in physics, but it was not in the area of quantum computing. It was in the area of accelerator physics, which is also fun. You know, it's a different kind of fun. Everything in particle accelerator physics is big. For example, the biggest particle accelerator is in Switzerland. It's called LHC, Large Hadron Collider. I forgot how many miles long, but it's a very long tunnel filled with equipment, and tens of thousands of people work on that experiment, actually, just on different pieces, different aspects, and it's discovering very, very basic things about nature. So that's my PhD research was in that area, and I worked in a large collaboration, and it was great. But then I discovered that I like to work on smaller projects that I would have the control of the entire thing rather than one small piece. And that's when I found this postdoctoral research opportunity with Professor Monroe. And so it was actually a pretty significant change in terms of how I do the research, what I need to know to do the research. I had to learn a lot, but that was very, very fun.
Yeah, that sounds cool. And then, where do you see your research field expanding to? And like, what are some interesting topics that can be further explored within the next 10 years?
The new ideas in this field, they come up frequently, and a lot of times the ideas turn out to be impractical. But recently, my colleague Deep Gupta and I came up with what we think is an interesting idea, just like a very different design for a quantum computer that uses atoms and ions at the same time. So these are different sort of, usually these two systems don't interact. There are people working with atoms, there are people working with ions. We think we have an idea of doing a combined system or a hybrid system, and we're trying to get funding to do that. If we end up with funding to do this research, I think this will be something very, very new, very exciting, and hopefully also will be a fruitful research. At least the way I see things now, that's hopefully one of the major research directions that I will follow in the next 5 to 10 years, and we'll see what comes after this.
And then going back to like your journey through research, where did you start? So like what were basic lab positions or internships that you had?
So, as I mentioned, my undergraduate degree is not from this country. And also, it was early 90s is when I did my undergraduate degree. There were no such things as internships. So that it's just a different system. So unfortunately, I don't even have any of that. Let me dial it back a little bit. So there are no internships, but during my undergraduate studies, in Russia, I was able to participate in an international exchange program with US. So I did come to the US as an exchange student for almost a year. And actually, I worked in this accelerator physics lab in Michigan. I didn't study, actually. My visa did not allow me to take classes for some reason, but it allowed me to work in the lab and get research experience, which was actually how I ended up doing my PhD in that lab. But I mean, I would say that's probably not something that can happen now. The world is different. And also there are international internship opportunities in my field, and at least I know of a few. And I know of some students who have done them in Germany, like similar to REU, but in Germany.
And then how did you find your passion for research? And how would you suggest a high schooler try to find their own passion?
That's a tough question. I think for me, it was just growing surrounded by people who are researchers. So growing up, I didn't even think about any other careers. I don't know. I mean, maybe you should consider a career of an artist or a career of a doctor or a lawyer, whatever. I didn't have people like that around me. And I guess my interests were shaped by those people who were researchers, who were physicists. My mom is a physics teacher, and my brother, I have an older brother who's a year and a half older. And so we were almost, the same age. He was just slightly more ahead of me. And I kind of, in some ways, I followed what he was doing because he was interested in chemistry. And so I kind of followed that. Actually, he didn't end up doing chemistry or physics. He's a programmer. He got interested in applied math and then computing, coding, and so on and so forth. I mean, some kids do have their parents, who are scientists, but I don't think you can, in a systematic way, find passion. It's like finding love. You don't do that. But if you think that science, be it physics or biology or chemistry, computer science, is something that might interest you, you can try reading. There's a lot of popular science books. Start with that and see if that ignites your passion or it seems boring. If it seems boring, it's probably not something that you would want to do, because these books are usually written to be exciting.
So really just like following whatever interests you?
I would say yes.
And then what type of traits do you think define a great researcher? And what type of traits would you look for in a potential lab member?
There are different types of great researchers, and I don't think there is one set of traits that works for everybody. I have had dozens of students who worked in my lab at various times, and they're all different. And, there are students who are very thorough, very careful, they plan ahead, and then, they do a great job. But occasionally, at least from my perspective, I'm not like that. It feels like their progress is very slow. They end up getting there, they end up getting great results, and they're very good scientists, and that's a great trait. But sometimes the person is not as careful, but They say, okay, let's try doing this. Let's do it quickly. Let's see if it works. There are different types of scientists. So I think there's no single recipe that will work. What I always found is that enjoying it, really, not doing it because somebody told you to do it or because this is your job or because your parents told you you have to do this research or whatever. Doing it because you are enjoying it, because you like it, is probably the most important. That's what I'm trying to encourage my students to think about. And if they don't feel like this is something that they love and they enjoy, then maybe they should think about what else they can do. I don't kick them out of the lab, but I give them opportunity to think about.
Yeah, okay. And then just for a final question, what's some advice that you would give to a high schooler who wants to go into physics?
So physics is unlike some other natural sciences, such as chemistry and biology, for example. Physics is based on a relatively small number of very fundamental concepts that you have to understand, not memorize, but understand. Unlike chemistry, where you have to memorize properties of elements, there's no concept there. You have to memorize it. Or like biology, you have to memorize all the, I don't know, classes and so on and so forth of animals. So in physics, you have to understand these concepts. And then if you do understand them, then you can be successful in a physics. Also in physics, you have to start from the basic things like mechanics and then build up to kinematics, kinetic theory of gases, and so on, and thermodynamics, electricity and magnetism, and kind of being able to systematically go from learning the basic concepts to more advanced concepts to the next step is the best way to proceed. And in practice, what a high school student can do is take AP courses. They will teach you these basics of physics. There are opportunities to network with students who are like-minded, who are interested in similar things. And I think that's very important. My son is also a physicist. Well, he's a physics student. And I know for him, it was when he was a high schooler, it was very formative. There was like a little physics club in his high school.
Yeah, okay. So
Okay.
that's all the questions that I have for today. And thank
All
you
right.
so much for meeting with me.